Hello, I'm Leon Conrad. Welcome to session 14 in this online course taking you through George Spencer Brown's Laws of Form. This is one of the high points in the course, the culmination of a lot of things that come together. And chapter 11 is often the bête noire, the stumbling block that people come across. The number of times I've heard chapter 11, I don't get it, is quite significant. And you know what? I was in that group as well. Even when I was studying the work under George Spencer Brown, I found chapter 11 very difficult. And he would say, just read the chapter. It's good advice. But even that wasn't enough. I needed a couple of keys from people like Graham Ellsbury and Walter Tydex to unlock key elements of the chapter. And what I'm going to share with you here is my understanding of it. Other people may have different understandings of it. But this is mine. And to start with, I'd like to take you through some definitions of some key concepts because they relate to how words are being used in this chapter. When we talk of expressions being finite, being infinite or indefinite, what do we mean? Well, for me, finite expressions are ones that have beginnings, middles, and ends. They're definite. You can point to them and they can be defined. Indefinite expressions are ones that have beginnings, middles, but no end. They go on like a beam. And infinite expressions, well, they have no beginning, no end. Spencer Brown was very fond of J.M. Robertson's work, Letters on Reasoning. I've referred to this in previous sessions where he actually quotes from it in one of the footnotes to his work. And there were two dictums he used to quote verbatim. The first was, there can be no rational ascription of single mode to the totality of things. And the second was this, terms of relative mode cannot rationally be used absolutely of an endless series absolutely considered. Worth learning by heart, but worth also understanding. Because this is how the thing appears in context. And with this, Robertson just kills the whole free will debate in one fell swoop. It's a brilliant piece of work. But before it and after it, he's using the words infinity and infinite in particular ways. Now, in the first instance, he's referring to his first dictum. Previously, he's talked about the totality of things. Here, he's talking about the infinity of things. So, for him, infinity and totality, or the infinity, the totality of things, are one and the same. It's almost like a Neoplatonic monad. Not one, but unity. In the context where he talks about an infinite series, which is itself not thought of as one of two or more correlative modes, then the series extends either indefinitely or it relates to an infinite series. And in the context, he's obviously talking about something that is absolute, like will. He says, you can talk of weak will and strong will, but the terms are meaningless because you're talking about will, and will is an absolute. It doesn't have an opposite. And will as an abstract term, which does not have an opposite, and that's very unusual, is a really interesting thing to contemplate. Now, at the back of all this is something Spencer Brown was very aware of. He quotes from Wittgenstein, which we cannot speak, one must therefore be silent. Spencer Brown goes against that. And he says, even though the composer knows about music and knows they cannot express what music is, and even though a mathematician loves working with numbers and maths and they can't express what maths is, that doesn't mean that the composer shouldn't compose music, and the mathematician shouldn't come up with new theories and ways of expressing things using numbers. And that is at the heart of his work. He has this notion in the background of his thinking that there is this mystery, this absolute, that cannot be described, and now what can you say about it? Let's make music. Let's count. And one of the reasons I say that when Spencer Brown uses infinite, he means indefinite, is this quote from page 53 of the 2011 edition. It comes just after a diagram. From an infinitely extended expression comes a potentially endless emission. So if there's an expression, it has to begin from there, and the emission goes on endlessly, indefinitely, rather than infinitely. So having sorted that out, we can then go into his work. He introduces Canon 9 in this chapter, which states that a demonstration rests in a finite number of steps. You can count it. You start counting it, you go on until you reach the end, and then you stop. Now, what are we counting? In an algebraic expression, each variable, so A, B, C, D, whatever, represents an unknown or immaterial number of crosses. And we know that you can have crosses that signify no cross at all, or you can have crosses that extend indefinitely. It's not possible to count arithmetical steps, but we can still count algebraic steps, as long as at least one count is finite. And that, for Spencer Brown, is equivalent to no step. So, with that in mind, consider this expression, and consider it extending further in a nested way. Now, Graham Ellsbury argues that the A term can extend indefinitely, and this can extend the expression. But what is the value of the basic element? If we take 4 permutations that are possible for the 2 states A and B can be in, and plug them each into the form, here we've got mark for A, unmarked state for B. We've got cancel, cancel, and that renders down to the marked state. In the next permutation, we've got the form, we do the substitutions, both marked, and we do cancel, cancel. It reduces to the unmarked state. In the third permutation, we've got A as unmarked, B as marked. We do cancel, condense, cancel, and we've got the unmarked state. Here, we've got A as unmarked, B as unmarked. There's the form, we plug in the values, and we go cancel, 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 and we're left with the unmarked state. So what is the value of the expression? Well, it's both unmarked and unmarked, but we can't say it's both. We have to say it's either marked or unmarked exclusively. Now, let's take this expression again, and we're going to take a number of steps. First step, we're going to duplicate it. We're going to confirm it using C5. And that gives this expression. Then we're going to put by C1, mark over the left-hand B term. That creates 2 divisions, and you know where we're going from here. We're going to do a sneaky thing. We're going to take the expression and put it inside itself. Well, that has this next to the left-hand A term and the right-hand B mark with transposition. Then, Spencer Brown says, we're going to take C4 and we get this. This is a step that puzzled me for years. I could not get it. You see, we've got an A mark, B mark, that's fine. And then after it is an A, can't find that. But how does this A result in a B mark? I tried everything. I tried extending the A's using C4. I tried doing other things. Didn't work until I thought it's either going to be a typo or there is a reference he's made to the classification of consequences, and he says you can mix and match them. So maybe that's what's happening here. Maybe it's a hidden Easter egg. Maybe he wants you to go on a treasure hunt. And if you do, let's see what happens. We need to find that the expression with A mark, B mark over 2, B mark, is equivalent to B mark. Can we? Maybe not using C4, but maybe using a variation of it. This is what we're setting out to prove. Can we do it? Let's see. Let's take the left-hand side of the expression, and we're going to put C1 mark over mark on the B term. That allows us to use J2, our old friend, and B mark appears to the left of each of the terms in the two divisions. The B mark duplication condenses to 1. We cancel the mark over mark and we're left with this. Now we've got something that is exactly equivalent to C4. Even though the terms are different. In C4 you've got A mark, B mark over 2A. And you've got an A under 2 levels and A in the space outside. No mark and an even number of marks are equivalent. And the term in the middle is under an odd number of divisions. You've got exactly the same thing in the expression on the left. You've got the B being the deepest space, in the deepest space and the shallowest space. On the left it's under 2 divisions, on the right it's under no divisions, and you've got the A in the middle under a single division space, an odd number. So we can say that A mark, B mark over 2, B mark is equivalent to a single B mark. Now we go back to our expression and see that this C4 variation applies here. We've got the left-hand side, and we can see how Spencer-Brown has derived the right-hand side and the reduction from this. It works. Now, what we do is cancel C1, and we've proved that the expression can re-enter itself, and this is a different quality to it than just the indefinite extension. So this expression can not only extend, it can do so indefinitely. Now, what is its value? This is the interesting thing. Let's call the expression itself f, and we know that this expression can be either marked or unmarked. So we're going to leave it for the moment and consider it marked, because if it's unmarked it just disappears. We don't need to consider it. And we're going to assign the 4 values to A and B that we did before. Here is the basic we're working with. We plug in the values, and what do we do? If f is marked, then it condenses, and if it's unmarked it disappears. We cancel, and we're left with the marked state. If both of the variable terms are marked, then we plug them into the expression. F condenses if it's marked. We cancel, and we're left with the unmarked state. In the third permutation, we plug in the values A unmarked, B marked. Now, here we cancel. F is marked, it cancels, and there's another cancellation that gives the unmarked state. If F is unmarked, then there are 2 marks at the second level which condense, and it also renders the unmarked value. What if both of the variables are unmarked? Well, plug them into the expression, cancel, and we're left with F, and we know that F is either marked or unmarked. So the whole value of this expression is either marked or unmarked inclusively here. And that's the difference. It's a both and. It has a different quality to it. And as soon as you get a both and, you're in the realm of the liar's paradox. A man says he's lying. Is he lying? Or is he telling the truth? Work that one out. In mathematics, this relates to the square root of minus 1. There are various assumptions that Spencer-Brown states you have to take into account. Firstly, that a number can be positive, negative, or 0. And it's interesting he thinks this way because he wrote a dictionary of musical tunes using this system. A note can be the same as a starting note, it can be higher or it can be lower. And that's how he classified the beginning openings of tunes. Wrote a whole dictionary about it. The second assumption is that a non-zero number that's not positive must be negative and vice versa. He also assumes that we know and accept the basic rules of mathematical operations. So this is the expression he starts with. X squared plus 1 equals 0. One of the basic rules is that whatever you do to one side of the equation you do to the other to retain the equivalence. So we're going to subtract 1 from both sides, which gives you x squared equals minus 1. If we divide by x to simplify the x, and x squared by x, we get x equals minus 1 divided by x. Now, x is on both sides of the equation. So if we plug in a value of plus 1 for x, we end up with an answer of minus 1. If we plug in the value of minus 1, we end up with a value of plus 1. How can that be? How can plus 1 equal minus 1 and minus 1 equal plus 1? Aha, say the mathematicians. We have an imaginary number, an image. This brings us into oscillation and time, because if something can be both and, it's going to switch values, and that switching is an action that takes place over time. It's like a verb. We've stopped thinking in terms of nouns, we're now thinking in terms of verbs. This expression we know reduces to a mark. So we're going to copy it across and look at this further. Now, if the P is equivalent to a mark, then the left-hand expression cancels, part of the expression cancels, and the P remains on the outside. If P is an unmarked state, then we plug the values into the expression and all we're left with is the mark. But the mark is the constant token, not the variable one. And if P is a variable and oscillates, what you get is a switch in position. And this is what brings us to the next part of the thing, time. And he introduces this sequence of events. And it's really difficult to get it from a static presentation in the book. You've got to read across T1, T2, T3, T4, T5, T6, and then it starts again at T7 at the top left. I'm going to take you through it, looking at what happens, but we're going to start at the top right and read down in rows going from left to right across. And I'm going to talk you through a sequence that goes inside, outside, spread. Look at what's happening. Inside, outside, spread. Inside, outside, spread. And I've used red to denote the white or unmarked state and blue to denote the dark or marked state. This diagram shows not static phases but a constant movement. Let's go through it again just for clarity. Inside, outside, spread. Inside, outside, spread. And what he does here is show how this relates to a waveform. And you've got to see this as travelling across. It's like notes, it's a musical score. You read the melody across, the harmony down, and it forms one whole. T1 is here. And you've got the spread. Then you go to the inside, and then the outside face. But there's a constant motion, so you have to read it diagonally down and see the waveform moving. And he then talks about frequency. What governs the change? Well, this representation of value is described as the frequency of oscillation. Where the speed is constant, the frequency of oscillation is determined by the length of the tunnel. He has this tunnel burrowing underneath the form. He goes into another dimension. And where length is constant, the frequency of oscillation is determined by the speed of its transmission through space. So, if you've got a tunnel yay length, the faster you go through it, the faster your answer will appear at the end. If your speed is constant and your tunnel is shorter, you'll get to the end faster. If it's longer, you'll get to the end slower. It's very basic stuff, really. But then he says, what's important to remember is that there is velocity. Representation of value has a direction. It doesn't go forwards and backwards, it doesn't stop, it doesn't have a break for lunch on its trip down the motorway. No. And he used to say, time doesn't travel backwards. Even when you're remembering something, the act of remembrance is an act that takes place as part of a forwards movement through time. So, expressions, functions, they're looking at the same thing here. Depending on which point of view we regard them. So he has this thing about the fixed and the volatile, the static and the movable, the expression or the function being one and the same in the form depending on how you see them. Now remember we had marked, unmarked and consequential expressions. Well, here we're going into real and imaginary values. And he puts this diagram in, which is equivalent, in my view, to this. And where there's a switch, a pulse, it reduces to this. And if you put different values for A and B in, you'll see that this emerges. It's a good exercise to try out on yourself, on your own. Now, what's important when we're plugging memory things into an equation is to remember that certain things will work, certain things won't. We must maintain the same level, the same value. Evens go to even, odds go to odd. We cannot have evens going to odd and vice versa. And this takes us into the modulator function of the calculus. And as soon as we go into flow and time, we can build engineering circuits. So this can be represented thus. And it's difficult to see it in this way. It's much easier if you rotate it through 90 degrees. And here you see you've got A and B at the bottom, and they can flow upwards. They've got two options. They can join, and those joined expressions can branch off and join single expressions, A and B on the sides. And then those single expressions can join together at the top. So, if you take from the top down, you draw a mark, then you contain two separate markers for A and B. Within those separate markers, you have a joint A and B that can go that way or that way, and there's your expression. Now, it's much easier to visualize how things are going in a circuit, which travels over time, if you've got a visually intuitive rendition of it in the simplest possible way. And this is what George Spencer Brown came up with. It's a work of genius. It reminds me of a word game you can play, and this is a good bridge into what's going to happen next. If we want to get from laws to form, we can do so by changing one letter at a time. Laws can change to lawn, lawn can change to larn, yes there is a word larn, Lan can change to lawn can change to law can change to for can change to form. And obviously the rule here is to use words that do exist. This is what's happening in this circuit. I'm not going to use the diagram from Spencer Brown's book. I'm going to use a diagram that Walter Tydex came up with in a talk he gave at the 50th anniversary conference celebrating the first publication of Laws of Form in 2019. It's also published on his website, and I'll put the link in the comments to the video, or just below the video. Now, you've got outline boxes representing the input and output, and solid boxes representing the switching elements. And what's happening here becomes clearer with reference to something that George Spencer Brown put in the paper that he wrote based on a talk he gave, which was an introduction to reductors. And you can see that he's got a waveform in 4 phases, or 4 stages that go through 4 phases of transformation. And he's linked it up with binary notation codes. 1 for up, 0 for down, for each one. Now, if we look at the difference between D and phase 1, anything that stays the same in the first 2 bits of the waveform the same doesn't change. Anything that's different switches from the top value to the bottom one. So we've got same, different, different. In the next 2, we've got same, different, there's the switch, same, different, and there's another switch. In the next 2, we've got different, same, same, and the different ones are switched. In the last one, we've got same, different, those are the switched, same, different, those are the switched. And that is how he changes one waveform to the form of another. And that is exactly what's happening in this diagram. Each of these waveforms has 4 sections. You've got to divide it visually into quarters in your imagination. So what happens when A goes to B? Well, you've got different, same, different, different. And that gives you waveform B. How does it change to C? Well, you've got different, same, different. How do you get from C to D? You've got different, same, different, different. And from D to E, you've got different, 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 different. And the same thing, E to F. Different, 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 different. Now I've taken you alphabetically A, B, C, D, E, F along the top. The thing is, this waveform can travel anywhere through the circuit. It can take any path it wants, and it will have the same result. There's magic in this system. What's interesting to note, going back to Spencer Brown's paper, is that he notes that the even phases are complements and so are the odd phases. And even odd is very, very much part of the Pythagorean view of number, the Platonic lambada, and it's interesting to note that in the construction of his diagram, you have different levels. You have a single level, then an even level, then another level, and there's this triangle geometry to it. I think Spencer Brown is thinking in these terms. Whether consciously or spontaneously, I don't know, but I think there's a link here between the Platonic lambada diagram and what Spencer Brown is doing in his system. It's something I'm intrigued by and may well look at a bit more. He then introduces a simpler format of it, and I think if you put the top markers in between the pairs and follow the lines and look at the way the waveforms change, you'll be able to solve this by yourselves. Now let me take you back to the word diagram. And if we colour in the letters that have changed and rearrange them by transposition, we get laws in form. Spencer Brown finishes off the chapter with a coda. We've reached the tail end of the chapter. And in this tail end, he says, we are and have been all along deliberating the form of the first distinction. So we've come full circle. The whole account of our deliberations is an account of how it, the first distinction, can appear in the light of various states of mind that we put upon ourselves, which is reminiscent of the Ouroboros diagram, the snake eating its tail. Eating its tail, it generates itself. It feeds on itself and generates itself. It's like a baby biting its toes in order to sense itself. And this diagram is from an alchemical source. The image is in the public domain, and the inscription inside is in Greek, and it means the all is one. And that is a fitting place to leave the session, coming full circle to the beginning of the work. But that's not the end of the main body of the work. We still have one chapter to go. Spencer Brown was very fond of cycles of 12. And perhaps that's why he put this extra chapter in which he outlines 4 experiments, which I'll take you through in the next session. Hope you can join me then.